Okay, so this so the presentation is called Double Machine Learning for Causal and Treatment Effects. I guess we try to be creative with the title right here. So it's based on two papers, mostly on the second one. Also having the same title. It's a joint work with Denis Chetverikov, Esther Duflo, Christian Hansen, Mert de Mirrer, and Whitney Newey. It was put in the Archive 2016. It's a fairly simple paper, but it took many people to write it. So it's and then we have another paper which is very complicated, and it's forthcoming in Econometrica because of this. It's called Program Evaluation and Causal Inference with High-Dimensional Data. It's joint work with Alex Belloni, Ivan Fernandez-Val, and Christian Hansen. Okay, so I'll be mostly focusing on the second paper. I'll be mentioning what some of the items that are covered in the first paper. So our goal here is to provide a general framework for estimating and doing inference about a low-dimensional parameter theta naught in the presence of high-dimensional parameter eta naught. So this high-dimensional nuisance parameter eta naught will be estimated with the new generation of non-parametric statistical method, now branded as machine learning methods. I resisted the terminology for a long time, but then I gave up finally. I said, fine, machine learning. So these methods include random forest, boosted trees, lasso, ridge, neural nets, boosted trees. You could also consider aggregated versions of the estimators or cross hybrids. For example, you can run a lasso, take out a smooth strand, and then fit a forest to residuals. That's going to be a cross hybrid. And so if we would like to use methods like that to do estimation of a high-dimensional nuisance parameter, and the target will be some low-dimensional parameter theta naught. We would like to construct good estimator for theta naught, as well as construct confidence intervals for theta naught. And of course, we build upon and extend the classical work in semi-parametric estimation, which also analyzed a similar problem where you have a low-dimensional target parameter and you have a nuisance parameter, which is estimated by traditional non-parametric methods, such as kernel regression and things like this. So this goes back to work of Bickel, Rita Wellner, in econometrics, Andrews Linton, Newey, Robinson, Rodnitsky, van der Waart, van der Laan, Rubin, and many others. So oftentimes, the way they handle estimations of nuisance parameters, they say, well, under certain conditions, these estimators will fall in a nice set, a Donsker set. It's a set whose complexity is bounded, so the complexity of the function set does not increase with the sample size. And in fact, this actually rules out most of these methods that are listed here. So for example, if you take these assumptions, like the estimators take values in a Donsker set limits the complexity of the function space, and this basically rules out all the examples that we see here, like all the high-dimensional examples. So we would like to go beyond those Donsker classes, and we did a bit of work on we and others did a bit of work on lasso, which goes back to like 5 years ago or something like this. There we used very heavily the structure of lasso. There's been relatively little work on using other machine learning methods, and so this is what we would like to do now: is to try to push this. This problem to other machine learning methods. And today I'll make two main points. Point number one is that the machine learning methods, like off-the-shelf machine learning methods, seem to be remarkably good in terms of prediction. However, good prediction does not automatically guarantee that you will have good performance for estimation in an inference about some causal parameter or low-dimensional parameters. In fact, the performance can be poor. So that's going to be a negative point, which will serve as a motivation for the positive point, which is that by doing double machine learning or orthogonalized machine learning, combined with some sample splitting, and we can construct high quality point and interval estimates of the causal parameters, low dimensional parameters. And I will illustrate these points in a partially linear model. It's a nice running example. Later on, I'll generalize it to moment condition models. So here we have the outcome variable y. We have a treatment variable d, or policy variable. So this is the policy or treatment variable. Theta naught here is going to be the target parameter of interest. Z here is going to be a high dimensional vector of other covariates called controls or confounders. And these, called controls or confounders depending on the department in which you sit. And then Z here are the confounders in the sense that D is related to Z. So conditional expectation of D is equal to M naught of Z, and M naught is not 0, right? So as will typically be the case in observational studies. In perfectly set up randomized control trials, this M naught vanishes, and many problems disappear. Otherwise, but otherwise they do appear, and this function is not equal to 0. Okay, so we have this set up, and so what I do next? I take a good prediction rule based on this model. So, for example, I can build one using random forest. So I can build a prediction rule for y using d and z, and obtain a prediction rule d theta hat naught plus g hat naught of z. It's obtained by combination of least squares in random forest. Right, so I can iterate on least squares in random forest and obtain this estimate. It respects the partially linear form. It has excellent predictive performance for predicting y using d and z. Why does it have in this example? Well, in this Monte Carlo example, I have a g naught z, the true function, generated as a linear combination of trees. So random forest is great for approximating functions that are linear combination of trees. So it works very well for predictive performance. However, the estimate of this low dimensional parameter that we get here is not so good. So if we look at the finite sample distribution of theta hat naught minus theta naught, the estimator minus the truth, the finite sample distribution is shown by this blue histogram, and you see it's biased relative to 0. Now it's not a crazy estimator. This one is not a crazy estimator, but it's heavily biased, and inference using this estimator could be quite misleading. Certainly, we could hope we could hope for a Gaussian shape like this, centered at 0, but what we have instead is this, and then it's clear that the inference using this distribution, well, using this estimator could be misleading unless we can somehow bias correct it or something. So, so this is the prediction again. So what's happening here? Like this is a good estimator for prediction purposes. It's a regularized estimator. In order to optimize prediction, this function is heavily regularized. It's kind of pressed down towards 0 a bit, and because of this regularization happening in this part, it has a non-trivial effect on estimation of this other parameter here. So this estimator is biased, and it's primarily caused by the regularization bias happening here. So in some sense, it's like it's analogous to the emitted variable bias here, except that it's a regularization bias, right? Okay, so how can we fix this? Well, we can fix this by double machine learning, and that's the second point here. So we can predict, we can solve 2 prediction problems instead of solving 1 prediction problem. So here we will predict y using z, and we will predict d, the treatment or policy variable, using z. Obtain the hatted quantities, these estimated functions. So here we're using random forest, but we can also use other best performing machine learning methods. Then we residualize. So you take y subtract of predicted value, take d subtract of predicted value, and then you regress w hat on v hat to get theta naught check. So this is like a Frischwall-Lavelle style approach to estimating the target parameter. In case you didn't know, the Frischwall-Lavelle was a machine learner who worked back in the 30s. And so, so now this distribution of this estimator, theta hat naught check, looks like this. So the blue histogram shows the finite sample distribution. It's centered around the true value, approximately centered around the true value, and the shape of the distribution is approximately normal, right? And if you look at the risk of this estimator and the risk of this estimator, yeah, this has a smaller variance but very big bias. This has larger variance but almost no bias. The risk of this estimator is smaller than the risk of the previous estimator. So this would be a better estimator. And plus you get the confidence intervals with this estimator. Okay? So this is the double machine learning here. Right? So we're solving two prediction problems, and we're using the results to construct the estimate of the low-dimensional parameter. So what's going on in these two approaches? Well, we can look at the moment conditions associated with these two approaches and analyze these moment conditions. In econometrics, we like to work with moment conditions with JMM, right? So so the first approach is based on this moment condition. So it's kind of a regression adjustment condition. So it's y minus d theta naught g naught of z times d. So given g naught, this equation identifies theta naught. So this is, think of that as a regression adjustment equation. The second approach is based on these residualized quantities. So we take y and subtract of predicted value, take d subtract of predicted value, and so on. So this one is a regression adjustment approach. And this approach we can call the Frischwall-Lavelle, or we can also call it the Niemann orthogonal approach in the sense that the scores or moment conditions that we use satisfy the Niemann orthogonality condition, which I'll describe later. So I'll explain this terminology, why we use this terminology. It also happens that this score here that we see is actually a semi-parametrically efficient score for estimating theta naught under homoscedasticity. There's also some other equations that you can use, for example, propensity score adjustment. But this will also not work so well for the same reason this approach doesn't work. I'll explain why. Okay, so let's focus on this or this. These are the two moment conditions that underlie our two approaches. So both of our approaches, they generate the estimators of theta naught by solving the empirical analogs of these moment conditions 1 and 3, where instead of the unknown nuisance functions, we plug in the machine learning based estimators of those functions. So we have G naught in the case of this moment condition. We have M naught and L naught in the case of this moment conditions, where L naught is the conditional expectation of y given z. Right? So we have two conditional expectations entering this moment condition. So we analyze these two estimators. So the estimator based on the moment condition 1 can be written as least squares of yi minus g hat naught zi on di. So this is the formula, and we can rewrite this estimator minus the target times root n as the sum of two terms a and b, a plus b. A is going to be approximately normal and centered at 0 by the central limit theorem, and term B is a kind of a biased term. It's a biased term. It contains this estimation error, and we can further approximate. Like if we do some sample splitting, if g hat comes from a set aside sample, we can do a simple approximation where we can approximate as B by an expression like this. So what did we do? We took di and replaced it by the conditional expectation m naught of zi. Right. So this is not this quantity is not 0. And here we have this estimation error. So heuristically, if we think about this problem heuristically, this is the estimation error in this high-dimensional or non-parametric setting. This error is going to be of order n into the power of minus phi. Phi is going to be between 0 and 1/2. And so you have a sum of n terms. You're dividing this by root n. And the term b will scale like root n times n into the power of minus phi. So it will diverge off to infinity. So it means that this estimator, the prediction-focused machine learning estimator theta hat naught, is not going to be root n consistent. It's still consistent, but just it's not going to be root n consistent, and it will have, because of this bias. The bias dominates and pushes theta hat naught too far away from the true parameter. So basically, the estimation based on this moment condition doesn't work so well here. Also, you could make a similar argument for the second moment condition where you do. So this is called the regression adjustment. There is also the propensity score adjustment where you take d and subtract of the predicted value here. So you just kind of do this. This approach will also not work. So let's look at the second approach. Why does it work? So for the second approach, we get an estimator, which is the least squares of one residual on the other. So the residual, so the one residual is the residualized y, another one is the residualized d. And under mild conditions, we can rewrite this estimator minus the target times root n as the sum of three terms: a star, b star, and another term which I'll discuss later. The term a star is going to be nicely behaved, so it's a sum of independent centered variables under conditions that permit the central limit theorem. This will be approximately Gaussian, centered around 0. And now you have another term which is the bias term. So the bias is still here, but now the bias has different structure for this estimator. It has a product. It has a product of the error estimation errors. So there's an estimation error for the conditional expectation of y given z, and this is estimation error for the propensity score for the conditional expectation of d given z. So that there's a product of two estimation error, and so potentially it's a good news because before we had one estimation error appearing, and now we have two estimation errors appearing here. So this is smaller. This is smaller term. So if we do back of the envelope calculations for b star, roughly speaking, it will scale like root n times n into the power of minus phi m plus phi l, where these two terms are the rates of convergence for estimating m and l. And oftentimes you could get these rates to be faster than n into the power of 1 minus 4. And so from these back of envelope calculations, from these heuristics, we could guess that the double machine learning estimator theta hat naught check is going to be root n consistent and approximately centered normal quite generally. But of course, how generally depends on your own definition of things. Obviously, it's going to be root n consistent and approximately centered more generally than the previous estimator, but there's still serious limitations here. So I don't want to oversell it, but it's going to be a lot more robust than the previous approach, and so this claim will be true under some formal conditions. Okay, so we could make this conjecture, and we can prove this actually as a formal result under formal assumptions to be stated later. Now I did mention these two terms, a star and b star. There's also a third term, and in order to have a nice behavior for this third term, and to have wide coverage of all kinds of machine learning estimators, we have to rely on sample splitting. So we rely on sample splitting to get the third term to be stochastically vanishing with only the rate restrictions. So by using sample splitting, we eliminate conditions that bound the entropy complexity of the realizations of machine learning estimators. Okay, without sample splitting, life would be very difficult. Okay, so so the question is why sample splitting here? So we have these three terms, as I said, and if we look carefully at this remainder, the remainder here contains terms that look like this. So it's a summation over I of ui times the estimation error for estimating m naught. And if we don't do sample splitting, this estimation error can depend on ui, and the analysis becomes very difficult. So it's still possible to do the analysis. You just have to write down explicit rates at which the entropy bounds grow. So we have to say that, well, you have to be very explicit, and you have to make heavy use of the assumptions. For example, when we did the analysis for Lasso, we had to rely on approximate sparsity assumptions, very explicit conditions that allow us to limit the degree at which ui and this estimation error talk to each other, right? So this is all done. So if you're interested in some ugly mathematics, we have a paper in doing the results without sample splitting, and it's forthcoming. So it's just, yeah, you have to, like, it's hard, yeah, you have to write explicit bounds and things like this. But then it's very hard to check those conditions for, like, if I give you a hybrid of random forest and lasso, if checking the conditions on the entropy of the realizations of these estimators might be difficult in practice. So in order to avoid doing this, we can rely on sample splitting. And with the sample splitting, what's happening is that this estimation error is independent of this. And so you can use just Chebyshev inequality and the fact that this is going to be, well, and as long as this is consistent for this, this term is vanishing. Like, very simple, right? So with sample splitting, it's easy to control and claim this is stochastically vanishing term. So without sample splitting, we need to use maximal inequalities to control the supremum of the empirical processes that look like this. So we take the supremum here over m falling in a set script mn, where script mn is the minimal function space that contain, or function set that contains the realizations of this machine learning estimator with probability 1. And so we need to control the entropy, the rate at which the entropy of this set grows. And it does grow in modern high-dimensional settings. The traditional assumption that people use, like if you, I guess in econometrics, you open Don Andrews' handbook chapter or Newey's handbook chapter, they assume that this set is P. Donsker. It doesn't work. It doesn't work. Or I guess Van der Waart book also has the same assumption. So it doesn't work. So we need to control the rates at which the entropy grows. It's fine. We can control it, but it's just practically it's very difficult to verify these conditions. So anyway, so we get rid of these conditions here, and then go back to the analysis of our two strategies, one based on the moment condition 1 and one based on the moment condition 3. So why does one strategy work and another doesn't work? I guess the key, I think, in our view, the key difference is the condition we call the Niemann orthogonality condition. And the condition is that if we take our nuisance parameter, so these are two regression function is our nuisance parameter, the true value is denoted by eta naught, and we compute the directional derivative of this moment condition with respect to of the moment function with respect to this nuisance parameter. So formally, it's the Gateau derivative, right, of this moment function with respect to the nuisance parameter evaluated at the true value. This derivative vanishes. So for the moment condition 3, this derivative vanishes. So what this means heuristically is that the moment condition the moment condition remains valid under local mistakes in the nuisance function. So small perturbations of the nuisance function, they don't change the moment condition too much. And this makes sense because in practice, well, you don't know the true value. You're going to be plugging in some approximation to the true value, and you need reduced sensitivity of the moment condition with respect to the plug-in, right? And so this is the condition. In sharp contrast, if we compute this Gateau derivative for the moment condition 1, the other moment condition, the obvious one, with respect to the nuisance function g, it's easy to see that this derivative does not vanish. So the two moment conditions that we had, they have the very different robustness structure. This is not a robust moment condition with respect to perturbations of g naught. And this moment condition is robust with respect to the perturbations of these nuisance functions. Likewise, you can also show that this second moment condition here is not robust with respect to the perturbation of the nuisance function here. So the robust one is this one. It's one of the scores that has this robustness properties. So the Niemann orthogonality here is the key. And we will use that to generalize this example. So we know that we need to work with score functions that have this structure, and then under some conditions we can do fruitful inference on the target parameter theta naught. So we carry out this generalization. We say we're going to work with moment condition models of this form. General abstract form. So theta is a vector valued generalized score function or moment function. Theta naught is a low dimensional nuisance parameter. Eta naught is going to be a true value, well, denoting the true value for the nuisance parameter living in some abstract convex set T equipped with some norm. It could be a function or vector of functions. We require that this score here, psi, has the Niemann orthogonality structure. So formally, so here we define this pathwise or directional derivative, the Gateau derivative operator, and then we require that this derivative vanishes. So it's an operator indexed by directions. It needs to vanish. So it needs to vanish along all permissible directions. And again, so heuristically, these conditions means that the small deviations in nuisance functions do not invalidate the moment conditions. We also rely on sample splitting. The sample splitting, if 1 through capital N denotes a set of all observations, then our letter I denotes the main sample, the set of observation numbers of size little n that will be used to estimate theta naught. I complement is going to be the auxiliary sample. It's going to be a set of observation names of size capital N minus little n used to estimate the nuisance parameter. And we assume that I and I complement, they form a random partition of the set 1 through capital N. Again, the use of sample splitting allows us to simplify the analysis enormously and cover a wide range of machine learning estimators for the nuisance parameter. Then we have a bunch of regularity conditions that are more or less standard, right? So there's like parameter not on the boundary condition. There are some mild differentiability conditions. The Niemann orthogonality condition that we just stated. Identifiability condition. We need some mild smoothness assumptions on the score function, but the smoothness assumptions are permitting scores that, for example, use in median regression. So some non-smooth scores are allowed. So here it's kind of much weaker form of smoothness. And then there are some rate conditions related to how fast the moments grow. Okay, and also there is a pointwise entropy condition, which is a more or less standard condition because well, it's and in principle, if we use smooth score like the differentiable score functions, we wouldn't even need that. Okay, so all of these conditions are more or less standard. So it looks messy here, but if you with some work you could deduce that the rate of convergence here needs to be faster than n to the minus 1/4. Then we form this orthogonalized machine learning estimator theta hat not check. It's going to be indexed by the sets I and IC, right? It does depend on how we partition the data to carry out the estimation of the main parameter and the nuisance parameters. And the estimator is going to set to 0 the empirical analog of our moment condition. Because this psi may not be differentiable, you may not be able to set it exactly to 0. So therefore, we need to write this more general stuff here. But basically, the idea is that we're setting this as close to 0 as possible. And the main result is that under the assumption stated, this estimator is going to be, after scaling by root n and some other stuff, this estimator is going to be approximately linear with the influence function psi bar given by this expression here. And it's going to be Gaussian, centered Gaussian. And the result is shown uniformly over the set of probability measures that live in a set script Pn, and the set is allowed to grow. So this explains the complexity of some of the notation. The analysis is uniform. It's actually uniform over an expanding set. Now, if you look at this estimator, there's a square root of little n here. And obviously, you can deduce from that this estimator is not fully efficient because it doesn't make the full use of the entire data set. So this is the reason why people don't like to use sample splitting. You lose some efficiency. However, you can restore the efficiency by doing the following. So we can do, say, 50-50 split of the data into equal parts, obtain the first estimate that I just described. Then we can reverse the roles of the main and the auxiliary sample. So you just switch the I and IC here, obtain another estimate. And then you average the two estimates. And both of these estimates will satisfy this expansion. And then, so you can deduce from this theorem as a corollary that this will attain the full efficiency. So you would be able to replace little n here by the capital N. And you can generalize this to a k-way split of the sample. You can also do extensions to quasi-splitting because well, if you work with moderately large sample sizes, then it's tempting to still cheat and kind of use the main sample to pick the best machine learning method, right? So maybe you train a bunch of machine learning methods on the auxiliary sample, but you'd still like to verify their performance on the main sample. And you can, in principle, do this. So you can pick the winner based on the main sample. Of course, this breaks the pure sample splitting, so the entropy is back, but the entropy is back in a gentle way because so kind of gentle means square root log of m way, and so the results go through as long as this rate of convergence for the non-parametric part of the model times square root log m goes to 0. So the results hold up under this quasi splitting. So again, so here we are not doing pure sample splitting, but it's a way to split the sample in a kind of controllable way, in a nice way. I have 5 minutes left, so let me mention a couple of things. So why do we call this Niemann orthogonality? So this idea of constructing scores that have this orthogonality property, they go back to the work of Niemann back in the 50s and 70s, where he was, I guess his problem was that he was he was working with a likelihood problem, parametric likelihood problem. He was having a nuisance high-dimensional nuisance parameter beta, and he was interested in the efficient inference on theta, the main parameter. And instead of beta, he didn't have MLE. He used something else, like as a plugin, right? And of course, so he asked the question, can I get the full efficiency somehow? And the way he constructed his estimator, basically, he said, well, I can use the original score, then I can correct the score. I can subtract all this term times this parameter mu, where mu can be rewritten in terms of the elements of the information matrix. And this correction, what it does, it still allows me to identify theta naught, the target parameter, but it has this additional structure, right? So this orthogonality structure, and this allowed him to solve the empirical analog of well, to construct the estimator for the main parameter, where he used arbitrary plugin for this nuisance parameter, not a maximum likelihood estimator, but some other plugin, like maybe a badly behaved one. You still needed some rate conditions, but this could be much worse behaved than the maximum likelihood estimator. And so actually this was generalized. This construction was generalized, like in semi-parametric settings. You can construct scores like this that have this property by taking original scores and projecting them onto the orthocomplement of the tangent space induced by the nuisance function. So if you're interested, you can read up to van der Waart, or you can read with Chamberlain. So there's this. So these ideas do generalize to fairly general framework. And we have a bunch of examples worked out. One of them is average treatment effect in a partially linear model that I just talked about. Another one is average treatment effect and average treatment effect for the treated, where you have a binary treatment, but you have no restrictions on this function. And so you're interested in this average treatment effect or average treatment effect for the treated. There are orthogonal scores that you can have there. They're also same as doubly robust scores. We also did the extensions to local average treatment effects and local average treatment effect for the treated, and some other examples as well. And all of this works, so all of this is practical. I mean, there were many theorems, but all of this was put to an empirical use. So here's an example quickly. So here we're interested in estimating the impact of 401k eligibility on net total financial assets. So Y is that. D here is the indicator of working at a firm that offers a 401k pension plan. Z includes a bunch of controls listed here. Data the data is due to Pater et al. And so here we estimate the partially linear model and the interactive model without restricting the effect to be without imposing the partially linear functional form. You see 5 columns. So this random forest here means that we have estimated nuisance functions by random forest. Here by post-lasso, here by boosted trees, here by neural net, and here's we use quasi-splitting to pick the best machine learning method to estimate the regression function for Y and regression function for D. And it turns out it's actually it's a kind of hybrid. So for estimating the regression function of Y on Z, you use lasso, but to estimate the propensity score, you use neural net, because neural net works better. And so this is there, and you could see that the numbers are fairly close to each other. They're quite robust, and so on. So it kind of works in a way that we would expect from the theory. So let me sum up. So we provided a general set of results that allow root and consistent estimation and provably valid asymptotic inference for causal parameters using a wide class of flexible modern methods for nonparametric estimation. The construction relied on 3 key elements. Number 1, the use of Neiman orthogonal estimating equations. Number 2, we needed fast enough rate of convergence of estimators of nuisance functions. And number 3, we had to rely on sample splitting to have the conditions stated just in terms of rates, and this allows the wide coverage of the machine learning methods without exploiting heavily too much the structure of the estimator.